Welcome back, everybody. This is Mr. Johnson with you once again. It's been a little while. This is lecture 14 on enthalpy, lecture 14, part 1. And we're starting with section 4.4 in our ebook, page 197, which is about endothermicity and exothermicity. But we'll be focusing primarily on 4.5 enthalpy. A couple of changes with this lecture. I'm wearing a long sleeve shirt, which I don't normally, not just because it's fall, but got a couple tricks up my sleeve, and I don't want you to be able to see those just yet. All right, I've flipped my page. I'm now on page 198 of the ebook, looking at this section here titled The Energy of Chemical Bonds. And this phrase down here that's highlighted, which says, bond breaking requires energy input, while bond forming results in energy release or an output of energy, is a really key statement that is going to underlie the majority of the concepts that we're going to talk about in this unit, thermochemistry, or thermodynamics. But before we get into bonds, I want to talk about forces, attractive forces. And I've got two magnets here that are attracted to each other, much like two atoms in a bond would be attracted to each other. And we'll learn later why, if we don't know, atoms are attracted to each other in a bond. It is also true to say that overcoming attractive forces requires an input of energy, whereas forming or strengthening attractive forces results in an output of energy. And that can be modeled by me trying to overcome the attractive force that exists between these magnets. Again, we could pretend these are atoms that are bonded, and it clearly takes energy to overcome that attractive force. I had to put energy in to pull those apart. And the energy that it took for me to overcome the attractive force between these magnets came from kinetic energy, came from the movement of my hands. It's kinetic energy that overcomes the attractive forces. And if these were atoms bonded and the bond were to be broken, which requires an input of energy, that would come from the motion of another molecule that hits it. It would come from the kinetic energy of another molecule that collides against these atoms that are bonded and that are attracted. Oh goodness, this is hard. And that are broken apart. On the other hand, if I were to let these two magnets come together to form an attractive force or to strengthen an attractive force, they would fly toward each other. And what that does is release energy. What it does is makes these particles move faster as they're accelerating inward, and that is a release of kinetic energy. So forming attractive forces or forming bonds releases energy. It transfers the potential energy into kinetic energy because it's making things move faster as they move toward each other, whereas overcoming attractive forces or bonds requires an input of energy, which is typically coming from kinetic energy as well. So again, breaking bonds requires an energy input, while forming bonds results in energy release, or forming attractive forces, even if they're not bonds, releases energy, whereas overcoming attractive forces, even if it's not a bond, requires energy. So I flip back a page, I'm on 197 of the ebook, and I've highlighted these three processes here, reactions we could call them, although this third process isn't technically a reaction. And I'm going to use these as examples of ways in which breaking bonds or overcoming attractive forces requires an input of energy, whereas forming bonds or forming attractive forces results in an output of energy, and how that corresponds with the delta H's we're seeing here. And we're also going to talk about what delta H means, what some of these units mean, and try to make sense of it all. All right, so we're looking at that first reaction, potassium hydroxide, solid potassium hydroxide. And the delta H is negative 57.8 kilojoules per mole. Well, delta H stands for enthalpy, change in heat or change in enthalpy. And the unit for enthalpy is always kilojoules per mole. And we'll deal later with what that means. Joule is the SI unit for energy. A kilojoule is 1,000 joules. Again, we'll worry about that later. It's negative, which means that there's a release of energy. There's a net release of energy from this process. It's an exothermic process. You might be thinking, well, wait a second, this looks sort of like a decomposition reaction. We're breaking things apart. And if you're breaking things apart or you're breaking a bond, shouldn't there be an input of energy? Shouldn't the delta H be positive? Well, there's more going on here than just a bond breaking. When an ionic solid is dissolved in water, which is what this reaction is depicting, solid potassium hydroxide is being added to water, creating an ionization reaction or dissociation reaction. There's actually three separate processes taking place. The first of those processes is that the liquid solvent, in this case water, has to spread out a bit to make room for the solute particles. And because all molecules are to some extent attracted to each other, we'll learn why later, they have what are called intermolecular forces. We are overcoming an attractive force, and that is a positive delta H. So the delta H for the spreading out of the solvent particles, in this case water, would be positive. The solute crystals, this would be the potassium ions and the hydroxide ions, also have to spread out when they get ionized or dissociated. And because there's attractive forces between ions, opposites attract, that also requires an input of energy. So that's also an endothermic process, or there'd be a positive delta H associated with that. And if that's all that were to occur, these particles spread out, then the delta H for anything being dissolved in water would always be positive. But the third process is the forming of attractive forces between the ions and the solvent, in this case between ions and water. Water's a polar molecule. We'll learn why later. There's a negative side to it and a positive side to it. So the positive side of water is attracted to the hydroxides. The negative side of water is attracted to the potassium ions. You're forming attractive forces between a solvent and a solute. And when you form attractive forces or form bonds, that always releases energy. Delta H would be negative. So when things dissolve in water, if the energy that's released from the solute particles forming attractive forces with the solvent is greater than the total amount of energy that it took for the solutes and solvents to spread out, then that process is exothermic. And that's the case for potassium hydroxide. The energy that's released when the potassium ions and hydroxide ions form attractive forces with water is greater than the total amount of energy it took to spread them out. But for some things, when they're dissolved in water, the energy it takes to overcome the attractive forces between the solute particles and the solvent particles are greater than the attractive forces that form between the solutes and solvents in the end, and therefore that's a positive delta H. So that's an example of how attractive forces require an input of energy, in this case the left-hand side of the diagram, and how forming attractive forces results in an output of energy. So here's the next reaction. This is propane combusting with oxygen to produce the products of combustion, carbon dioxide and water. It's telling us that for this reaction, the delta H of combustion, or the enthalpy, is negative 2,221 kilojoules per mole. So that's an exothermic process, and most combustion reactions are. But remember, in a reaction, for the reactants to react, all the bonds between all those atoms have to break apart. So to break all the bonds between the carbons and hydrogens, an input of energy is required. Breaking bonds requires energy. So the delta H for the left-hand side is going to be positive. On the product side, bonds are being formed between the carbons and oxygens and hydrogens and oxygens. And when bonds form, that is a output of energy. It's exothermic, so delta H is negative. And what in this case must be true is that if overall there's a release of energy, and we know that energy had to go in to break bonds and energy had to come out when bonds formed, that more energy is coming out from the formation of bonds in this case than went in to break the bonds. So that's why this reaction is exothermic, is because more energy came out from bond formation than went in for the breaking of bonds. And then in this last one, which is actually a physical change, phase changes are physical. We're going from solid water to liquid water. This is a gross misrepresentation of the arrangement of particles in a solid phase or a liquid phase. But when a solid goes from a liquid, you're spreading those molecules out a little bit. Water's actually not that way, but pretend it is. And if in that case you're overcoming an attractive force, because all particles, molecules are attracted to each other, that is going to require an input of energy, which is why in this case the delta H is positive. And the fancy term for melting in chemistry is fusion. So this is the heat of fusion, or the enthalpy of fusion. So we've flipped 2 pages ahead. We're now on 199 of the ebook, looking at this potential energy versus reaction coordinate or reaction proceeding diagram. And as a reaction proceeds, we always go from reactants to products. In this case, the reactants are at a lower potential energy state than are the products, and therefore there's an input of energy that is needed for that to occur. The delta H is positive. It's endothermic. And the reason why that would be, as we saw a bit ago in a combustion reaction, or this is opposite to that, is that it must be that it takes more energy to break the bonds for the reactants than the amount of energy that was released by the products. And that's what it says down here, is the energy absorbed to break bonds is greater than the energy released during bond formation in an endothermic reaction. So they have positive delta H values. We scroll down, we see the opposite, and see the reactants having more potential energy than the products. A delta H is negative, and in that case, more energy is released during bond formation than is absorbed during bond breaking in an exothermic reaction. Negative delta H values. All right, here's a multiple choice question that I'd like you to try to practice. And I'm going to try to embed a few more of these into our lectures to make them a little more interactive and to give you more opportunities to practice multiple choice questions, knowing that we're going to be seeing them on our unit tests. So take a moment to try to answer this one, and then come back after you pause the video. All right, I picked A. We see in this case that the delta H is positive. We'll learn what that little superscripted circle means later. That means that it's an endothermic reaction, and that means that more energy went in to break the bonds on the reactant side than came out when the bonds were formed on the product side. This phrase may not make sense yet. That's what we're going to get to here in a moment, but it could also be said the sum of the bond enthalpies of the bonds and the reactants is greater than the sum of the bond enthalpies of the bonds and the products. And we'll learn more specifically what that statement means in a moment. So I've skipped ahead to section 4.5 now, where we're going to be for the next three lectures. It's on enthalpy, and the order in which the information is presented in this section to me doesn't make total sense. So I'm going to present it in a slightly different order that will hopefully make sense to you. But before I start, I want to orient you a little bit now to what we'll be studying in this section, in this thermochemistry section. One of the things we'll be studying is why energy changes take place in reactions. And we've learned a little bit about that. It has to do with the difference between the amount of energy that goes in when bonds break versus the amount of energy that come out when bonds form. So that's a bit about the why. We're also going to learn that there's two different ways the enthalpy of a reaction, the delta H of a reaction, can be determined. One of those ways is theoretically. We can use numbers, tables. We can determine it theoretically. Another way is it can be determined experimentally. The second half of this unit will be how we determine enthalpies experimentally, and that technique is called calorimetry. This right now is about how enthalpies can be determined theoretically, how they can be determined from numbers, from tables. And there's three ways that enthalpies can be determined theoretically. One of those is using what is called bond energies or bond enthalpies. And the multiple choice question we just looked at referred to that. So one way to determine an enthalpy theoretically is through bond energies. It to me is the most sort of logical way to think about enthalpy, and it's a very common way that you're asked in chemistry to determine an enthalpy. A second way to determine enthalpy theoretically is using what's called heats of formation, and that's what the part 2 lecture will be about, using heats of formation. And the third way to determine enthalpy theoretically is through what's called Hess's law. So there's ultimately 4 ways you want to be able to think about and calculate enthalpies. Bond energies, that's a theoretical way. Heats of formation, that's a theoretical way. Using Hess's law, you don't know what that is yet, that's a theoretical way. And then using calorimetry, which is an experimental method for finding enthalpies. The rest of this lecture today is going to be about using bond energies or bond enthalpies to determine the enthalpy of a reaction. So we've jumped all the way to page 215 of the ebook or 207 of the textbook, and we're looking at this section called the use of bond energies or bond enthalpies. We already know that if a reaction is endothermic, delta H is positive. That's because more energy went in to break the bonds than came out when bonds formed. And the opposite is true of exothermic reactions. So if we're to try to find what the delta H value is and whether it's positive or negative, if we have access to the energy that it takes to break all the bonds, and we have access to the energy values it takes to form all the bonds, we can compare those numbers, and whichever is greater tells us whether the reaction is positive or negative. And that's what we're going to be doing, is using a table of bond energies or bond enthalpies that allow us to predict how much energy it takes to break all the bonds, predict and calculate how much energy comes out when all the bonds form, compare those values, and figure out what the overall delta H is. In our book, it tells us that bond energy is the enthalpy change required to break a given bond in 1 mole of gaseous molecules. For the values to be used that we're about to see, the molecules technically have to be in a gaseous state. but assume they are. Just for now, assume that they are. Something is really important about this definition. Bond energy is the energy it takes to break a mole of bonds. Because we know bond breakage requires an input of energy, all bond energy values, by definition, are going to be positive. But if we want to use that value for a bond that's forming, all we have to do is flip the sign. Because the same amount of energy comes out when a particular bond is formed as went in to break that same bond. And the units for these bond enthalpies are always kilojoules per mole, which will give us, in the end, the overall value for delta H in kilojoules per mole also. So let's see what this looks like. We're going to flip our page. All right, so here is this amazing table, table 4.5.2, average bond energies. And again, it's in kilojoules per mole. Notice it says average. We'll come back to that in a moment. Notice also that every one of these values is positive, because by definition, bond enthalpies are the energy in kilojoules per mole it takes to break a mole of bonds, assuming the molecules are already in their gaseous state, which we just assume they are. These values will not be necessarily true for any one molecule, which is why they're called average bond energies. The actual energy associated with a particular bond depends on the molecule it's in and its neighboring atoms. And that's what it says up here in yellow, is that the bond energy of a particular bond between two atoms will vary depending on the chemical environment it's in. This means, and I'm now reading the green bit, that bond energies typically reported are average bond energies over a large variety of compounds that give us a fairly accurate value. The importance of that, the significance of that will be addressed later, but just know that these are average bond energies. There's another Bozeman science video I'm going to have you watch later that helps us understand why some bond energies are greater than others, but it basically has to do with the attractive force. If the attractive force between two atoms is greater, it will take more energy to overcome that attractive force. And there's two factors. I don't know if you remember this from prior science classes. Two factors that influence attractive forces. This is called Coulombic attraction. It's how far apart those species are that are attracted to each other. The closer together they are, the more attracted they are. And also what their charge is, or how polar they are. The more charged or the more polar that particles are, the more attracted they will be to each other. And the closer together they are, the more attracted they are to each other. So that has a bit to do with why bond energy values vary. Notice that multiple bonds, double and triple bonds, are down at the bottom, and those bond energy values are generally greater. The reason why, and we'll learn more about bonds in our next unit, is that more electrons are being shared in double and triple bonds, creating greater charge and therefore a stronger attractive force. O2 is an OO double bond. The bond between two oxygen atoms in O2 is an OO double bond. So if you're ever looking for OO double bond, it's O2. And notice that carbon dioxide is such an important molecule that if you are looking at the CO double bond in CO2, you should use 799 instead of, in general, 745. Another trend to notice is in this red circle. The HF bond has a greater energy value than does the HCl, which is greater than HBr and HI. And that has to do with the sizes of fluorine, chlorine, bromine, and iodine. And we'll learn how to predict relative sizes when we get to our periodic trends unit, but the HF bond has the most energy associated with it because the distance between the H atom and F atom is the least. The closer that two particles are, the more attracted they typically are, and that's because F is the smallest atom of Cl, Br, and I. As we move to the right, those atoms get bigger from Cl to Br to I. The attractive force weakens and the bond energy goes down, as well as we can see in the bond energy table. So that's a little bit about why these bond energy values can vary. I've flipped my page. I'm on 217 of the ebook or 209 of the textbook. And I'm looking at this highlighted equation up at the top. This is an equation that is used all the time in chemistry, and what it's saying is the enthalpy of a reaction, the heat of a reaction, which will be in kilojoules per mole, by the way, is equal to the sum of all of the bonds that are broken, the sum of the bond enthalpies of all the bonds that are broken, minus the sum of the enthalpies of all the bonds that are formed. And I'm going to do an example problem with you, help you understand why this formula works and how we are going to use it. So here's an example problem for us. We've got nitrogen gas reacting with hydrogen gas to produce ammonia gas. And again, to use the bond energies, the reactants and products have to be gaseous, assume they are. You won't be asked to do this in a case where they aren't. You do not yet know how to draw what are called Lewis structures to predict what types of bonds exist between the atoms, nor their arrangement. So for the time being, until you're taught how to do this, I will give you, or we will give you, the structures of all the molecules in a problem where you're asked to use the bond energies. To do this, we need to know that the bond between the nitrogen atoms is a triple bond, because a nitrogen-nitrogen triple bond has a different bond energy value than as a double bond or a single bond. The bond between the hydrogens is single, and the bond between the nitrogen and the hydrogens in NH3 is also a single bond. I drew H2 out 3 times to make it clear that there are 3 HH bonds that need to be broken on the reactant side, and I drew NH3 out twice to show that in each NH3 there's 3 NH bonds, or a total of 6 in the 2 NH3 molecules. Now remember, we're talking about this at the scale of moles. So it's a mole of N triple bonds that need to be broken. It's 3 moles of HH single bonds that need to be broken, and 1, 2, 3, 4, 5, 6, we already know, moles of NH bonds that need to be formed in this. Down at the bottom, I've written the equation again for finding the enthalpy from bond energies, and it's the sum of the bond enthalpies of the bonds that are broken minus those that are formed. That equation should be somewhat intuitive to you because we know that the bonds that are broken are already positive. So we need to publish them as they are by not changing their sign. We publish them as they are because energy goes in to break bonds that are positive. But when we use bond energy values for bonds that are formed on the product side, we have to distribute a negative into them. We have to make them all opposite in terms of their sign for them to be valid. So that negative sign goes in front of the bonds that are formed. It doesn't for broken because as written, the bonds are already being formed, broken. So here's how I do this and how I show my work in a problem like this. And there's other ways to do it. I know that I've got to break an N triple bond, or a mole of N triple bond. So I look at my bond energy or bond enthalpy table, and I see down in the multiple bond section that an N triple bond takes 945 kilojoules per mole of bonds to break. I don't put kilojoules per mole in all my work, it's too much. I know they're all kilojoules per mole, and I'll put that at the end. So I'm going to put that in parentheses because that's what it takes to break that bond. And then I need to add to it 3, because there are 3 of these, 3 times what it takes to break a mole of HH single bonds, which is 432. Yep, 432. And that takes care of my bonds that are broken. So these are bonds broken right here. I then need to subtract from that the sum of all the bonds that are formed. And there's only one type of bond form. It's an NH single bond, and there's 6 of them. So I say, okay, minus 6 times, maybe should have used brackets instead of 2 sets of parentheses, but that's all right. 6 times and an NH single bond is 391. 391. From 945 plus 3 times 432, I got 2241, positive, bonds broken. 46 times 3, 91, but with the negative distributed, I got negative 2346. Those are the bonds that are formed. 2241 minus 2346 is negative 105, because in this case, more energy was released from the bonds that were formed than went in for the bonds that were broken. It's an exothermic process, and the delta H is negative 105 kilojoules per mole. Keep in mind that when we're publishing the enthalpy of a reaction in kilojoules per mole, it is kilojoules per that reaction happening a mole of times. Not per mole of any one molecule, but per the reaction happening a mole of times. So I'm going to put per mole of RxN. That's kind of weird. What we're saying is if this reaction happens a mole of times, 1 mole of nitrogen molecules reacts with 3 moles of hydrogen molecules to produce 2 moles of ammonia molecules. When we publish an enthalpy for a reaction, it is as the reaction is balanced, and it is per that, again, reaction happening a mole of times. And I'll come back to that later when it becomes a little bit more relevant. So I encourage you to try practice problem 2 on page 218 of the ebook or 210 of the textbook. Pause the video. When you're done, come back and see how your solution compares to mine. Again, practice problem 2 on 218 of the ebook. I recommend you try on your own. And you'll need your bond energy or bond enthalpy table available to you as well. One thing to consider doing is being really careful about counting bonds. So what I did is on the reactant side, I crossed out how many CH bonds there were. And there were 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them, not 6. I got to change that to an 8. There are 2 CC bonds. Those are crossed out in red. And then in the O2, there's one OO double bond, but since there's 5 O2s, there's 5 OO double bonds. Did the same thing on the product side. In each CO2, there's 2 CO double bonds, but if there's 3 CO2s, that's 6. There's 2 OH bonds in each water. 2 times 4 is 8. So I've really carefully counted up all the bonds and written it out as such. The next step would be to publish the bond enthalpy values for each of these and do the math, and I'll show you what that looks like. So here's my work. Here's the 8 carbon-hydrogen bonds. Those values are positive because they're being broken. 2 carbon-carbon bonds, 5 oxygen-oxygen double bonds, which sums up to 6488, minus the sum of 6 CO double bonds, 8 OH single bonds, which is 8530, and then it's negative 2042. This is an exothermic reaction. Again, it's another combustion reaction, which are almost always exothermic. Another option, instead of having this negative in brackets and distributing the negative n, is you could just, for the products, publish the bond enthalpies as negative. I could have said negative 799 here, negative 467 here, ignored the negative out front, and that works as well. When you show your work for these problems, be sure that you're at least showing this bit here, the sum of the bonds broken and the sum of the bonds formed. That is it from me, but I'm going to tack on a short Bozeman science video with a really great explanation about why different bond energy values vary, what bond energy is. It's 6 minutes. If you're willing to watch it, I recommend you hanging in there. Been a pleasure serving you today, as always. Good luck, folks. Continue making the world an amazing place.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 52. It's on bond length and bond energy. Some of the first bond lengths ever measured were measured by scientist Kathleen Lonsdale, who was an X-ray crystallographer. She would put a solid crystal in front of X-rays, measure the diffraction. It told her a lot about the structure of that molecule, and she could even measure the distance between atoms. And that allowed her to unlock the structure of hexamethylbenzene, that famous benzene ring. She was able to determine that it was a hexagon, that it was flat, and she even measured the aromatic bonds. In other words, the single-double, single-double, single-double bonds between the carbons. And by measuring the length of that, that eventually led to this whole idea of resonance. So not only was she an amazing chemist, but she broke down a lot of walls. She was one of the first 2 females fellows elected to the Royal Society, first tenured professor. She was an amazing scientist, but she really got us down this road of bond length and bond energy. And so if we have 2 atoms, they're both going to be attracted to one another. And where does that attraction come from? It's the electrons of one atom being attracted to the protons of another. And so that's going to pull atoms together. But if they get too close to one another, then there's going to be repulsion. And we can measure these forces just using an energy distance graph, where we've got the energy that's pulling those or pushing those apart, and then how far they are physically separated. And using a graph like that, we're able to determine the bond energy, the energy holding them together, and also measure the bond length, how far those atoms are going to be apart. And so the bond energy, if we were to define it, is simply the energy required to break those atoms apart. Now, likewise, when we form a bond between the two, we're going to release energy, and that's just simply the negative bond energy. Now, the strength of that bond, or the bond strength, is going to be built upon the charges of the atoms themselves. The bigger the charges are, the greater that bond energy is going to be. And as we increase the number of electrons in a bond, so as we move from a single to a double to a triple bond, we're actually increasing the charges and therefore increasing that bond strength. And one interesting thing that you should know is that as we increase that strength, we're going to pull those atoms together and we're going to actually decrease the bond length. And so if we look at these 2 representative atoms right here, as we bring them close together, there's going to be attraction. In other words, as we shorten the distance between the atoms, as they get closer and closer together, there's going to be a greater attractive force. Now, as they start to get really close together, there's actually going to be repulsion between those 2 atoms that's going to push them apart. And so we can find what's called that Goldilocks, the point where they're not too close, not too far away, and we're going to have the highest amount of energy right here. And they're just going to kind of vibrate at that space. So if we were to look at 2 atoms, like 2 atoms of hydrogen, we would find that that energy to distance graph would look something like this. There's going to be attractive force between these two hydrogen atoms out here, but as we bring them closer and closer together, that energy of attraction is going to get greater. As we move them even closer, then we're going to move into this whole idea of repulsion. And so this is going to be that Goldilocks area right here. And so what we can measure then is the bond energy, the energy holding those atoms together. And likewise, since we've got distance here on the x-axis, we can measure the bond length, how far those atoms are apart. And so if we define what is bond energy, it's just two atoms connected together. And so bond energy is the energy absorbed when we break those atoms apart. Now, likewise, there's going to be energy that's released as we bond those together, and that's going to be the negative bond energy. It's going to be exactly the same. The amount of energy to break it apart is the same amount of energy that we get when those two atoms are going to be attracted together. Now, what contributes to that bond energy? It's going to be the electronegativity of all the atoms involved in that molecule. And so let's say we were to look at boron. Boron is going to have an atomic radius of 83 picometers. What does that mean? The distance from the center of that nucleus to the outside is going to be 83 picometers. And so if we were to connect a boron to a boron, we would anticipate that that bond length, the distance between the two atoms, is going to be twice that. It's going to be 166 picometers. But if we were to measure the actual bond length in a molecule, let's throw one up here, and it ends up being 175 picometers. In other words, they're farther apart than we would expect. That means that we're going to have a very weak bond between these two atoms. And so basically, as we increase that bond length, that distance between the atoms, we're decreasing the bond strength. Now, if we were to use another example, let's say we're looking at rhenium, which has a radius of 137.5. If we had two rhenium atoms, we would expect that that bond length is going to be 275 picometers. If we actually measure it in a molecule like this, and it's less than that, that means that they're really overlapping. There's greater charges holding it together, and so we would call that a strong bond. Again, the higher your bond energy is, the closer those atoms are going to be, and the shorter that bond length is going to be. Now, what happens as we increase the bond number? Let's say we're looking at two molecules that look essentially the same. We've got ethane, which is carbon attached to carbon, and then hydrogen around the outside, and then acetylene. And so this is the same thing, carbon attached to carbon with hydrogen around the outside, but in this case, we've got a triple bond right here. How is that going to affect the bond strength and the bond length? And so if we look at these two carbons, we've got one that's a single bond and one that's a triple bond. If we were to measure their bond length, we would find that as we increase the number of bonds, we're actually decreasing that bond length. They're getting closer and closer together. Well, what does that tell us about the bond energy? The bond energy is increasing over time. So again, the more electrons that we're sharing, the more charges there are, the greater that bond energy, and therefore the shorter the bond length is. If we were to measure the same thing with nitrogen, single, double, triple bond, we'd find that we're decreasing the bond length again. So what's going to happen to our bond energy over here? It's going to increase over time. And so did you learn to describe the energies involved in both breaking and forming chemical bonds? I hope so, and I hope that was helpful.